Good afternoon. We continue the first introductory part about machine learning, where we introduce the concepts of machine learning and the algorithms associated with them. And also today we will review some basics of math that is needed in this course. Last lecture we stopped at the classification, regression and classification. Today we start with clustering. Clustering actually is the same as a classification, where we classify data, but we don't have labels. So we don't have teacher to label that classes. So we need the machine algorithm to be able to classify inputs without labeling. So how this could be done? This can be done by looking for the similarities between data. Then they can cluster the data into two or three or more classes. Then, of course, we can have interpretation of the clustering after that. So clustering is one way for the unsupervised learning. Of course, we throughout this course, we will go through some details of clustering algorithms. Reinforcement learning, as we mentioned last lecture, as we mentioned that reinforcement learning, that we don't have a teacher, there is no teacher, but we have a critic. So the critic says that it is correct or wrong response. Then the machine can update its algorithm in order or as a response of that commands, like correct or wrong. Also, during this course, we will go through the reinforcement learning algorithms in more details. So the idea of the reinforcement learning, that we have the agent here, and then we have some environment that we have high uncertainty about the environment, and then we have sensors. We might have sensors, and of course the sensors looking for the output of the environment, like for example the movement of a robot. We might have noise or corruptions, and then the agent will read this sensor's data, and then will take action based on that sensor's data, and the environment will have like some feedback with some delay, that it is a reward or punishment, or to say that it is correct action or wrong action. On the long run, the agent can update its knowledge about the environment. And now we will go through a few applications of machine learning, just very rough applications. For example, disease progress prediction. So to predict how the disease progress will be. Then as we mentioned also last lecture, that we can have the database in the hospital. For example, when we have 1,000 patients attributes, and we look to the situation of patients, how the disease was progressed with them, and then the machine learning will try to learn the situation based on the attributes. Then we have learned machine. After that, then of course the learned machine, if we apply new data, new attributes patients, then the learned machine can or could predict the situation of the patient. Demand and load prediction. Also, this is one possible application as important applications for machine learning. For example, in electrical networks, we need always to have some prediction or forecasting for the load, which is uncertain actually, but it depends on many factors, like for example the weather and some other like factors. And then if we can accurately predict the load, then we can optimize the generation. Predicting number of train travelers, for example, this is one that is needed, of course, to predict how many travelers that will be. Predicting market demands, it is uncertain also, in order to produce the right quantity to maintain the price, for example. So how this could be done? Usually we have database about the history, then the machine learning will update its algorithms in order to base it on the database, and then we have an assessment, then we have predicted demand, then we have an assessment for the predicted demand and the actual demand. Of course, this the machine, after learning, it will give us some prediction or some suggestion about the demand, how it will be. But when the real demand comes, then we can compare between the predicted demand and the real demand, and then we can also update our database as well as updating our machine learning in order to learn more about this. Risk analysis and management. Before you go to any project, usually we need to study the risks and also the opportunities, of course. And we need also the risk analysis to reduce our uncertainty, because risks are associated with uncertainty. So as we reduce uncertainty, we can have, it becomes easier to have to make a decision. The worst case to take a decision when you have 50-50. So you don't know. Then you just flip the coin and then you decide to go to this project or not. But if we can reduce the uncertainty, base it on the machine learning applications, then it becomes easier to take decisions. When machine learning is not suitable, of course, because of this, machine learning now becomes like a very nice term, so many people try to apply them even in applications that they are not suitable for. For example, if for this tank model, as far as we can model it mathematically, so in that case, why we need to use machine learning to learn the level with those values? So as far as we can predict it accurately, then it is not needed. Of course, in some cases, if we have high uncertainties, it might be possible. But generally, machine learning is not like suitable for any application. We should decide what kind of application that we need machine learning and artificial intelligence. What are the risks of machine learning? We might have biased algorithms. Remember always that the quality of the machine learning algorithms depend on many factors. One important factor is the quality of data. If you have junk data, if you have biased data, if you have very low quality data, then you will have very low quality machine learning algorithms as well, or machine algorithms as well. So always we need high quality data. Also, we should have enough data, not only high quality, but enough amount of data, and spans the problem very well. So we might have biased algorithms. If we have biased data, some of the data are hidden, or we have manipulated data, or whatever. So in that case, we might have biased algorithms which not reflect the real problem very well. Also, some of the machine algorithms are black box, like neural networks, for example. Neural networks, we don't know how it works exactly. Of course, we know the algorithm, but it is not like transparent. So it is called black box modeling. In that case, in many situations, we cannot predict very well how it will work. So it might work with our data, but how it will work for some other kind of data. So we cannot be sure 100%. And in some critical applications, this is like a big risk. For example, black box or multi-layer neural networks like deep learning, for example, they are very nice to classify or to recognize between things, but I cannot use it for in a control system for example, a nuclear plant, for example. because you cannot predict very well how it will work in any situation. Lack of effective data, for example, in size or in the span of attributes, can cause problems as well. It might have overfitting or underfitting problems. Overfitting means that when we use the model is much more complex than needed, then we might have overfitting, where the algorithm starts to learn not only the data that's required, but also the noise. So in that case, we got overfitting problem. And underfitting when the model is lower than needed. So we need always to compromise. We need always to find what is the right model to be used. So this is one of the risks in machine learning, that especially when the problem is unknown, and we try with different algorithm sizes, for example, and we have limited data, so we don't know if it is the right algorithm or not. Misinterpretation of the resultant models. This is one of the problems of the machine learning algorithms. Lack of awareness. Okay, machine learning or machine algorithms can learn some situation, but also it reacts based on data without awareness. Every one of us heard about this Boeing 737 MAX with this tragedy for this Ethiopian Airlines. The sensor of the plane was giving wrong data. It was mentioning that the plane is going up. So the artificial intelligence or of the autopilot start to take the plane down. So it is Boeing, it is latest model. It means that they use the latest technologies, but we have here lack of awareness. So they don't know, because the decision is based on data. When we have low quality data, when we have wrong data, then the reaction will be wrong. So we have that disaster because of this problem. Another risk, it may replace a human in many working positions. For example, I read once that any human behind a computer doing some job one day can be replaced by this artificial intelligence. So in that case, we will have increase in unemployment rates. Okay. So you can think about more risks for the machine learning and for the artificial intelligence as well. As an exercise, there is a data in our model where we have two classes of data. You can find them like class 1 and class 2. What is required that try to visualize those data into two classes. For example, try to use whatever language that you like, but I like to visualize those data. For example, here I used Octave, that I can make two different colors, but try to use whatever you like, but try to recognize or to plot the available data. This is the first exercise that it is not needed to return the exercise to me, but try to do it. And if you have questions, then we can discuss them next lecture. Okay, as I mentioned in the previous lecture that we need some math for this course. Linear algebra is needed, optimization theory, and probability and stochastic process. Those are the main three topics in math. They are quite much required in this course. Today I will make just a review, fast review about optimization theory, and we will see some main concepts here. There will be also another course will be arranged by our unit in March or April about convex optimization. So I will send you the link to that course. So it is very much recommended to register that course. Okay. Yes, optimization. What is the optimization? What optimization means? Optimization means that we need to find minimum or maximum for certain function. Or it is, if we like to minimize, then usually it is called cost function. Always we try to minimize costs. Or if we want to maximize, then we call it like rewarding function or utility function. So usually we are looking for like maximizing utilities or rewarding, and we're always looking for minimizing cost functions. So if we have just simple cost function, like this one, for example. We have here the extreme points, or they are called also like stationary points. We have stationary point here, for example. We have a stationary point, and this is stationary point. Those stationary points, usually they are the extreme points. This, for example, is local maximum. Why I said local? Because there is another one maybe going. Yeah. So this, and this is called also local minimum, and this is also local minimum. Okay. If we look to this function, actually, the definition of the differentiation of this function refers to the rate of a change. Rate of a change. For example, if you take the rate of a change here, for example, this is f dash of x. If we take the at x1, for example, at x equal to x1, you can see the rate of change is going down. So this should be less than 0. Indicates that the rate of a change is going down. If you take the value here, for example, at x1, so f dash x at x equal to x, so x2, then it will be greater than 0 because the rate of a change is going up. So this is the concept of differentiation. Of course, here I went a little bit very basics, but just for those who don't have enough math background, we will use those concepts quite much in this course. So we need to have these. And for those who know those concepts, it is just like a review. So when it is going up, then the rate of change will be positive. Okay, and at this point, at the extreme points, usually the rate of a change equal to 0 because we're going down, then we reach to the bottom. At the point of the bottom here, we have f dash of x. If this is x3, at x equal to x3 is equal to 0. But it is the same also here. If it is x4, then f dash of x at x equal to x4 also equal to 0. So every stationary point, we will have the differentiation equal to 0. Then the condition here, if we like to find extreme point in our function, we need to find the point at f dash of x equal to 0. This gives us the stationary point. Now we are talking about unconcentrated optimization. Okay, so the differentiation at equal to 0, then we will have extreme point. The extreme point, as I said, it can be maximum, it can be minimum, it can be inflection point. It means that sometimes we might have like maximum, and it is going like this, and then it goes, for example, like this again. So this inflection point, or it can be like this again. So this inflection point is also the differentiation here equal to 0. So wherever the differentiation is 0, then we have extreme point. We have extreme point. This extreme point can be positive, can be maximum, can be minimum, can be inflection point. So this is very important concept to remember. Okay. In this review, it is, as I said, I will not explain, or I will not teach optimization here, but we just make fast review for some concepts. For the unconcentrated optimization, for example, this cost function equal to x squared minus 6x plus 8. As I said, now we are looking for the extreme point. We differentiate this cost function, and we found that there is extreme point at x star equal to 3. This is extreme point. But is it maximum or minimum or inflection? We don't know. Okay. How can we know this? Actually, one method, just by checking the second derivative. If we take the second derivative, f dash of x, the second derivative of the equation, you can see if the point was minimum, okay, the second derivative, it gives you the rate of change from this minimum. If it is minimum, it will change where up or down, it will go up. If it is minimum, it will go up. What it means that the second derivative will be positive. The second derivative will be, because it was already minimum. So the second derivative means that the second rate of change. So the rate of change of this derivative function, it will be positive because it will go up. Then the second derivative, if it is positive, greater than 0, then the point was minimum. If the second derivative, okay, if the second derivative was negative, it means that we were already on the top, and then the second derivative, that the rate of a change, it will go down. Then if the second derivative of the function less than 0, then it means that x, for example, this at x star. So x star here was minimum. If it is less than 0, then x star was maximum. If the second derivative equal to 0, it means that it was an inflection point. It was an inflection point. Why? Because the inflection point, as you can see, it is just like straight. So the second derivative is still 0. It means that we didn't go up or down. Okay. So those are very basic concepts, and I started with this one-dimensional problem to make it to understand the concept. Of course, after that, in this course we will discuss much more complicated cases when we have multidimensional problems. But just it is important here to understand the basic concept. Yeah. So you can see here, this is the situation of those three cases, for the maximum, for the inflection, and for the minimum. Okay. What about multidimensional or multivariate situation? Now, if we have more than one independent variable. Here we have only one independent variable, x. But in many situations, we might have f is function in x1 and x2 up to xn. So we might have multivariate problems. So in that case, it is multidimensional. Of course, to draw the situation, we can draw them if it is one dimension or only two dimensions. It's one like x1 and x2, and this will be cost function, for example. This we can plot also, but if it is more than two dimensions problem, then we cannot plot them. But they might be actually in practical we have always many parameters. Okay, in that case, just like extension for the single parameter or single independent variable case, it will be almost the same, but instead of talking about the derivative of one cost function, now we talk about the gradient. So the gradient of the cost function should be 0. What is the gradient? The gradient is nothing but just vector of the derivatives. So if we have n independent variable, then we differentiate that we take the partial derivative of the cost function with respect to x1, with respect to x2, until the partial derivative with respect to xn, and every one of those should be 0 at the extreme point, or at the stationary point. Okay. To be minimum, we need to check if it is minimum or maximum. We need to check what is known as the Hessian matrix. What is Hessian matrix? Hessian matrix is the second derivative of the cost function with every parameter. So you can see that the Hessian matrix is if the cost function is, we call it u, for example, then the second derivative of u with x1 and x1 the second derivative of u with x1 and x2, the second derivative of u with x1 up to xn. Actually, this should be c, not u, but I will correct it in the slides. But it is the cost function, and also the second derivative with the cost function with respect to x2 and x1 and so on. So this matrix is called Hessian matrix, and it gives us a representation of the second derivative of the multivariate function. Okay. Now, how to know is it maximum or minimum or saddle point? If the eigenvalues of this Hessian matrix is greater than 0 for all eigenvalues, means that, for example, if you have like 3 by 3 matrix, then we will have 3 eigenvalues. If all eigenvalues are greater than 0, then this point or this vector represent minimum. If all of them are less than 0, negative, then it is maximum. If we have minimum and max, if we have zeros, or we have positive and negative, then we have saddle point or inflection point. Okay, so this is a general extension for the previous equation. Let us take this example in case of unconstrained optimization in case of two independent variables. So we have this cost function equal to x1 x2 squared minus 2x1 squared plus x2 plus 5x1 x2. So now we can take the first derivative with respect to x1, we have this result. The first derivative with respect to x2, we have this result. Then both of them equal to 0. Then we have two equations into two unknowns. It can be easily solved, and we got the result. So we have here the result. We have three possible results, as you can see, that x1 star, x2 star, and x3 star. Okay. And now we built the Hessian matrix. So the Hessian matrix, we derive or we take the differentiation of this function now with respect to x1 again. So if you take the second derivative with respect to x1, then you will have, this will be 0, and this will be minus 4, and this will be 0. So here we will have minus 4. And if you take the second derivative but with respect to x2, so here we will have 2x2, this will be 0, this will be plus 5. So we have 2x2 plus 5 and so on. So now we have the Hessian matrix representing the previous problem. Okay. You can substitute for the first solution that we have in this Hessian matrix, and then we got this Hessian matrix at that point. Now we can compute the eigenvalues. The eigenvalue you can use, for example, any package like MATLAB or Octave or whatever to find, even it is not difficult to find the eigenvalue by hand in case of 2 by 2 matrix, but it is better to use calculators. And then we can, when we found the eigenvalues of this Hessian matrix, it gives us the situation of this matrix. So actually, when we solved this, we found one positive and one negative. One positive and one negative means that it is a saddle point. It is not maximum, it is not minimum for the x1. So it is just an inflection point. And if you make for the other point, then you can find also it was minimum for the second point and so on. So this is the function. This is the cost function in case of two-dimensional independent variables. Okay. In many applications, or in real applications, we always have constraints. We always have constraints. So it is very rare to have unconstrained optimization. What is the meaning of constraint optimization? It means that we need to minimize some cost function. Okay. It means that we are looking for the independent variables or the independent vector x that minimize certain cost function, and this x should belongs to some feasible set omega, but always we have some constraint. So those constraints that, for example, we have here inequality constraints that j1 of x should be less than or equal to 0. J2 of x should be less than or equal to 0 until Jm of x should be less than or equal to 0. And we might have also some quality constraints that h1, h2 until hk equal to 0. So this is one, and this is very, very important kind of problems that we will use them a lot in this machine learning course. For example, if you want to design some box, example, and you want to have certain volume of this box, but at the same time you want to minimize the area of the surrounding area, for example. So in that case, we can find what is that we would like to minimize. For example, this is x and y. Let's say x and y, and let's say this is x1 or x1, x2, x3. So you can see here that if you want to minimize, like the area here, so it is x1 times x3, and then of course it will be 1 here and 1 from the other side, so it is multiplied by 2, but we can ignore this, and also plus x2 times x3, for example. You want to minimize those, but if you say unconcentrate optimization, just minimize, so what will be the result? Simply the result will be 0. So you will have x1 equal to 0, and x2 equal to 0, x3 equal to 0. This will be, if we have here, x should be positive. So x here, x vector, should be greater than or equal to 0. Then we will have just 0, and this will be trivial solution. But if we want to design this box to have certain volume for this box, then we can say that where x1 times x2, for example, times x3 should be equal to, for example, 4 meters cubed, for example. In that case, this will be concentrate. This will be concentrate for this optimization. Then we like to minimize this, but we have this as a concentrate. This is the concept of concentrate that we need to achieve. So here we would like to minimize some certain function, but we have some constraints given, like inequalities, and also equality constraints can be both of them. In case that you have inequality, let's say we have x1 squared plus x2 should be less than or equal to 4. We should put it in the same form like this, because this we will continue in this course. So simply it will be like x1 squared plus x2 here minus 4 should be less than or equal to 0. So now we have the same form. So this will be like j1 of x, for example. Okay. If it was greater than, not less than, what we do? Just we multiply by negative sign both sides. So we will have minus, and this will be minus, this will be plus, and we will have the same. Okay? So just remember that to convert the form to be in the same form like this one. And always also minimizing any function f of x is the same as maximizing the negative part of that same function. So those are the same. Minimizing f of x is the same as maximizing minus f of x, or the reverse also is true. Okay? Now we have x equal to x1 up to xn, so we have vector of x. Here, T means here transpose. Transpose, for those who are not familiar with vectors, so x1, x2. When we say transpose, means that it is column, from column vector from row vector becomes column, like this. So the transpose changing the row to column or the column to row. Okay, what kinds of optimization problems that we have? We have several kinds. For example, the optimization problem can be convex or non-convex problem. We will explain what is the meaning of convexity. Linear or non-linear. It can be numeric or integer. For example, integer, we use integer programming or combinatorial problems. It can be polynomial or non-polynomial complex problems. It means that polynomial or non-polynomial means that when the complexity of the problem increases, the required computation cannot be represented by any polynomial function. So it will be like accelerated very, very high. I just give simple example. We have a problem with, let's say, with 4 parameters, okay, from x1 to x4. And when you want to solve this problem on your computer, for example, you will need, let's say, I will make it simple to understand. So it will take, let's say, 30 minutes, okay, to solve, to find the optimum point, for example. And if you have, let's say, 5 parameters, like from x1 until x5, and you want to solve the same problem, then the required time jump to be like 4 hours, for example. If you have, let's say, 10 parameters from x1 to x10, then you will need like 20 years to solve the problem. If it is 15 parameters, maybe it becomes like maybe 1,000 years to solve. So the problem complexity increases very, very fast. You cannot have a polynomial function that representing the required computation to solve the problem. Okay, so this is called NP problem, non-polynomial complex problems, which they are very, very well known. And for example, like chess game, for example, it is NP problem. Okay, what is the meaning of convexity? Convex problem, they are the simplest optimization that we can solve, because usually they have one stationary point, at least within the range that we are looking, okay, or within the feasible set that we are looking. We have only one optimum point, either minimum or maximum. Okay, so the concept of convexity is that the function itself is always less than a line, because it is a line, always less than or equal to a line like drawn over this function at any points x1 and x2. So you can see here, if you draw a line for between any 2 points, the real function will be always less than or equal to that line. What it means? It means that we will have only one optimum point or one stationary point if we are looking for the minimum. Okay, this one is non-convex, as you can see, because if you draw this line, we have this up above and we have this down. So this is non-convex problem. So this is the concept of convexity for looking for the minimum stationary point. In many problems, we might have too many minima or maxima, for example. In that case, if we have a problem that contain like one-dimensional problem, like this one, x, okay, and it was like this, and so on, and we are looking for the minimum point. So if we take the differentiation of this function, this is minimum, this is stationary point, this is stationary point, stationary point, stationary point, stationary, and so on. Okay. Of course, we are looking always to the minimum point, but if we use some searching algorithm, that it will stop when f dash of x equal to 0, and if we start here, okay, and we move, then our algorithm will stop here, and we say that this is the minimum, but we don't know if there's better minimum than this one. So this is called local minimum. Okay, then we can push this point to be out, and then we start looking for another one and looking for another one. Of course, this is easy because we have one dimension, but just imagine that if you have 100 dimensions of x, okay, and you have many minima in every point. So this can be NP problem, and you might supercomputer may need months searching for all points in order to find the optimum point. Of course, now we have many sophisticated algorithms like genetic algorithms and so on in order to find what is the optimum point, or at least satisfied point. So many times we are not in many real problems, we are looking for like satisfied solution, not optimum solution, because in many problems, in high-dimensional problems, we cannot prove that this is the optimum. In many applications, we say that it is like satisfied solution, or we say that it is optimum within some assumptions. Within some assumptions, if we put very strict assumptions, we can say that this is the optimum solution, but within that assumptions. But if we have convex problem, if the problem can be approved that it is convex, we are happy because we will have only one minimum, and once we find it, this will be the unique solution. So we don't need to go and look for other better solution. Okay, now how to solve such problem? How to solve this unconstrained or this constraint optimization? The way to solve this is by converting from constraint optimization problem to unconstrained optimization problem. How to do that? One method is called the Lagrange multiplier method. That, for example, this is the primary version of the algorithm, that LP equal to f of x. F of x is the optimization, is the cost function. As you can see, this is f of x. And what we do, we just add all unconstrained and inequalities and equalities to that problem. Yes, in this way. So we have summation. This is called Lagrange multiplier, lambda I, multiplied by ji of x from I equal to 1 to m. Ji of x are the inequality constraints, plus summation mu k multiplied by the quality constraints. Now we solve this as unconstrained optimization. We solve this as in the same way we did before with the unconstrained optimization. We will have some examples, and also we will have some comments, but after the break we can continue. We can have 15-minute break and then we continue. Hello again. So we continue about the Lagrange multiplier optimization. So as we mentioned in the first part, that we can build this unconstrained optimization. It is called primary version, because every Lagrange multiplier, it might have dual version and primary version, or dual form. So now we have the primary form is equal to the original cost function, plus we just sum the inequality constraints and multiply them by lambda I. It is Lagrange multiplier, and also the summation of what the quality constraints with multiplied by mu k is the Lagrange multiplier as well. And now we treat this as unconstrained optimization. We find the gradient of this LB with respect to vector x equal to 0, and also we need to differentiate this with respect to lambda, and also with mu and equal to 0 all. So the problem becomes how to minimize this problem, or this cost function, and we have, this is the constraint or the feasible set that x should be belongs to this omega feasible set. Okay. Now we just take into consideration our inequality constraints, okay, without loss of any generalization, because we can also add this as we will see later. Okay. Remember that this ji of x should be less than or equal to 0, and this lambda I should be greater than or equal to 0. If we found, when we solved this, if we found that this Lagrange multiplier lambda was less than 0, then that inequality constraint is not active. It means that we can put lambda equal to 0. It means that we remove that constraint, inequality constraint, and we can get even better result. It is inactive if lambda I associated with that inequality constraint is negative. Okay, so lambda I should be always greater than or equal to 0, because if it is less than 0, it becomes negative, and ji already negative, so this will be positive. So we are not minimizing that. We increase the cost function in that case. Of course, there is a proof for that, but we will skip it now because it is not the purpose here to explain in details how it works, but how to apply them, how to apply Lagrange multipliers for optimization, because many concepts in regression and also in support vector machines in machine learning based on those important concepts here. Okay, I like to explain this based on some example. So solve the following problem. So here we need to minimize x1 square plus x2 square. X belongs to real numbers, and subject to the constraints are x1 plus x2 must be less than or equal to 4, and also 2x1 plus x2 must be 10. So now we are looking for it. It is very simple problem, but at least we will explain some concepts here. So now we have constraint optimization, as I said in the beginning. So we need to convert this from constraint optimization to unconstraint one, which can be done in this way. So we minimize the cost function x1 squared plus x2 squared, plus we have this inequality constraint. We multiply it by lambda x1 plus x2 minus 4, as we said that this should be here to be less than or equal to 0. And for this equality constraint, we multiply by mu 2x1 plus x2 minus 10. Now we solve this unconstrained problem with how many parameters here? We have x1, x2, mu, and lambda. So we solve this, we differentiate this with respect to those 4 parameters that we have: x1, x2, lambda, and mu. For the mu, for this equality constraint, it doesn't matter. Mu can be positive, it can be negative, it can be 0. It will not affect the solution. But for lambda, must be positive. Lambda must be positive. Otherwise, this constraint is inactive, and we can put lambda equal to 0. It means that if we remove this unconstraint, if lambda is negative, then we can get even a better result. Okay, let us start. So we differentiate with respect with everyone. LB with respect to x1, with respect to x2, with respect to lambda, with respect to mu. And when we solve these functions with respect to x1, it becomes, you can just see here, if differentiate this with respect to x1, you will have 2x1. This will be 0 because we don't have x1, so it will be 2x1 plus lambda plus 2 mu. This will be the first equation. As you can see, 2x1 plus lambda plus 2 mu. And in the same manner, we differentiate with respect to x2 and with respect to lambda and with respect to mu. Now we have 4 equations in 4 unknowns. We can solve them easily because they are linear functions, all of them. So it can be easily solved. And when we solve them, we found that x1 equal to 6, x2 equal to minus 2, and lambda equal to 20. It means that it is more than 0, greater than 0, then, or it is positive, which means that this unconstraint or this inequality constraint is active, and the mu equal to minus 16. So now we have solved the problem. So this is the optimum. The optimum that x1 equal to 6 and x2 equal to minus 2. Let us try to substitute these values into the real problem, the original problem. So for this one, 6(1) equal to 6 and x2 equal to minus 2, 6 minus 2 equal to 4. Then we achieve this inequality. Okay? And x1 equal to 6, so 2 times 6 equal 12, x2 equal to minus 2, 12 minus 2 equal to 10. So the second inequality, or the second constraint has been achieved. Okay, what is the minimum point that we achieve now? The minimum point here is 6 squared is 36. 36 plus minus 2 squared is 4. Then the minimum point here is equal to 40. The minimum point is equal to 40 in this case. Okay. Now let us change a little bit. What happens if we put x1 plus x2? We need to be more than 4, not less than 4. If the inequality constraint is that x1 plus x2, we need to be greater than 4, not less than 4. Okay. In that case, if we solve the same problem, but we put this greater than 4, okay, then we will have negative lambda. We will have negative lambda. Since we have negative lambda, it means that this inequality becomes inactive. What to do? Just ignore it when you solve the problem. Okay, if we ignore it and we solve the problem without it, then we can even obtain or get better result by putting lambda equal to 0. And then when you put lambda equal to 0, then you solve without that constraint, just to solve minimizing with respect to x1 plus x2, so 2x1 plus x2 equal to 10, and I will leave this as exercise for you when you solve without this one, and you can see that you will get x1 and x2 better than, you can have less values for x1 and x2, and also achieving this will be when it was greater than or equal to lambda. So we have seen already the prime form of the problem, and we can also define the dual form. The dual form is interested in machine learning because in many situations we have a lot of attributes x, but we have less constraints. For example, if you have an image, okay, and assume that every pixel is x. So we have two dimensions, like image, and we have, for example, x11, x12 in this way. So we can convert from 2 dimension to 1 dimension. So if the image is 1 megapixel, then we will have 1 million x here, from x1 to x million. Okay, and we might have some constraints about the image. So we might have, let's say, 20 constraints, and now we would like to optimize. So in order to make the same concept here for the prime form of the Lagrange multiplier, you need to differentiate with every x, and also to take the differentiation with every lambda, for example.
You might want to use a different color pen. That red doesn't really show up.
Okay. Yes. I will use different one. So we have here, we have here image, for example, and then we convert from 2-dimensional vector or matrix, for example, of the image to 1 dimension. So we might have 1 million elements, and differentiating, taking the gradient of the function with respect with 1 million element can be like highly it will require high computation, but in the dual form we can have the differentiation or the derivative with only with the Lagrange multipliers alone, which can be much less in many situations. This is the reason that we go to the dual form of the problem. So if we take the linear case, simple quadratic form, that we like to minimize x for the double summation, means that it is like minimizing x transpose times a times x. A contains those elements from a11 up to an, okay? And this is called quadratic form problem, so we like to minimize this one, subject to these like inequality constraints. So this can be done in this compact form, so that minimize x. We are looking for the x which minimize this quadratic form, subject to hx minus p to be less than or equal to 0, and actually will be the same as we have done before. So this is the prime form of the Lagrange multiplier. It is X transpose AX plus lambda. Lambda here is a vector, contains all the inequality constraints. We have M inequality constraints here, times HX minus P. So now, as we said that we are looking for the positive or the maximum lambdas, so it is like maximizing for lambda and we minimize for X. If we solve for the primary equation, primary problem, so we differentiate LB with every X, then we have, this will be the optimum X. So the optimum X is equal to minus half A inverse times H transpose times lambda. Lambda, of course, should be lambda hat. Okay. Now we substitute this into the original function. When we substitute this in the original function, you can see that we got to maximize minus 1/4 lambda transpose times lambda minus lambda transpose times P. And because we have negative here, as I said that maximizing the negative, it will be like minimizing the positive. So it will be minimizing over lambda this function. And you can see in this function, X disappeared. We don't have X here. So it means that we need only to optimize with respect to the Lagrange multiplier only. And this considerably reduce the complexity of the problem in case that you have a lot of independent parameters X. As I said in the image case, when you have maybe millions of X and maybe you have few number of constraints, in that case it is better to solve this problem instead of solving the original problem. But both of them should give the same solution. Of course, there is a guarantee that they should give the same solution if the original problem is convex, like this quadratic one is a convex problem. Okay, we take example to explain this concept. So we like to minimize x1 times x4 plus 2x2 squared plus x3 squared, and we have only one constraint. x1, x2, x3 plus x4 should be greater than or equal to 5. To put this in the original standard form, so we take this 5 here, but we need to be this than or equal, not greater than or equal, for this reason that we multiply the whole inequality constraint by negative, by -1. So we have the same in the standard form. Then this is the primary version, or the prime version of the Lagrange multiplier. We take the partial derivative of LB with everyone. In the beginning, I will solve it in the conventional way. Then I show how to solve it in the dual form and to see how much the problem complexity reduced. Now, when we solve this in the conventional way, we need to take the partial derivative of LB with respect with x1, x2, x3, and x4, and also lambda in this way. Solving this, we got lambda equal to 20 divided by 11, so it is positive, which means that this inequality is active, and then we have this optimum solution. So the optimum solution is x1, x2, x3, and x4. We got the optimum solutions. Okay. Now, if we just apply the dual form that we minimize with respect to lambda, with this equation, so we have already A, we can derive A from the equations, and also we have only single inequality constraint, so we have single element lambda, and if we substitute this in this equation, what we obtain is only that function. So minimize with respect to lambda, 1/4, 5.5 times lambda squared minus 5 lambda. So we need to take the derivative with only one parameter instead of 5 parameters. So taking the partial derivative, or actually in this case we don't need to have partial derivative because we have only single parameter. So the derivative of L, the dual form, with respect with lambda, we got lambda equal to 20 divided by 11 as the original solution, and then we just substitute to find the optimum x. We need just to substitute. We don't need to make the whole derivative story again. Of course, here also we have some problems. Sometimes it is not easy to find the inverse of a matrix A in some situations, so we need to use some numerical methods to find the inverse of matrix, especially if the matrix is ill-conditioned. Okay. The last part in this introductory lecture is I just collected many formulas that will be used or might be used during the course. So here you can find some just general formulas like what we mean by identity matrix, what we mean by transpose, orthogonal matrix, for example, and some norms when we talk about norm, and what is the meaning of linear dependency or independence. Okay, what we mean by rank of a matrix, because actually matrices here in this course are widely used. Singularity and non-singular matrix. What is the meaning of eigenvalues and eigenvectors? So it would be good that if you can go through those, or at least during the course when we talk about something, so we will mention if it is already in those definitions here. For any matrices, for example, A and B, A times B transpose equal to B transpose times A transpose. Those actually definitions are well known in linear algebra, but I can understand that if some of you, they have been like many years, they didn't see or they didn't use those, they easily forget those concepts, but we need them in this course. So some theorems also, yeah. Singular value decomposition, actually this is, or eigenvalue decomposition, they will be used, especially when we talk about some support vector machines, or how to clean data. When we show how to clean data, we will use a lot of those concepts given here. Yeah. So you can see, for example, if I give like A matrix times X vector, and you want to differentiate with respect to X, this will be A transpose. If it is X transpose times A, it will be A. X transpose times X, the differentiation. So you can see that it is equal to X, and so on. So those are some like definitions that you don't need to memorize them, of course, but you might need sometimes to go back to those slides to see how to use and why. For example, if I derive something and you was just trying to understand the process, then you can go and see how to do it. For example, how to differentiate scalar with respect to vector. So y equal to function, and this function is function in vector x, okay? And you want to differentiate y with respect to this vector. So we have this shape, if x is even a matrix, for example, in this case. So J here is called gradient matrix, and so on. That's all for the introductory part in this course. So we have just introduced the main, what is the meaning of machine learning, and also we have seen some concepts of regression, classification, clustering, and reinforcement, and also we just review some very basic concepts in optimization and in like concentrate optimizations. So this is very introductory part for the machine learning course. The course started. It will start like to the main topic next week. So next week we start with the supervised learning, which is the first and one of the most important types of machine learning algorithms, where we start by the regression and then we go to the neural networks, and to see also we will see some important applications. Any questions? Okay. Thank you very much. Thank you.